Okay, we're going to talk about Chapter 8, Periodic Properties of Elements, and we're going to begin by summarizing Chapter 7. We saw how Planck used quantum numbers to predict wavelengths of light and blackbody radiation. We saw how Einstein used a particle model of light, later called photons, to explain the photoelectric effect. And Bohr provided the first model of the quantized atom to explain emission and absorption spectra for hydrogen, but it only worked for hydrogen. De Broglie reasoned that if light behaved mostly as a wave, but in some experiments revealed particle character, could an electron, thought to be a particle, have wave character? Davison and Germer did an experiment and discovered that a beam of electrons could be diffracted. Heisenberg came up with his uncertainty principle that we can't know both the position and velocity of an electron. And another way of saying that, because velocity is proportional to kinetic energy, is to say you can't know both the position and energy of an electron. Schrödinger wave equations applied to electrons can be solved to give probability distribution maps, or orbitals, of the electron's position. And these wave equations yield three interrelated quantum numbers, n, l, and m sub l. N can be any integer equal to or greater than 1 and corresponds to the Bohr model energy levels. L has integer values from 0 to n minus 1 and relates to the shape of the orbital. The shapes are given letters to designate them S, P, D, F, corresponding to L values 0, 1, 2, and 3. M sub L is a quantum number that defines a specific L orbital and ranges from minus L through 0 to plus L. So what do these shapes look like? The S orbital is spherical, and it applies to any n value 1 through 7. The L quantum number for an S orbital is 0, and the M sub L for an S orbital is always 0. P orbitals range from n equal to 2 through 7. L equals 1 for a p orbital. M sub L could be minus 1, 0, or plus 1. Each of the three p orbitals is designated with the M sub L quantum number minus 1, 0, plus 1. D orbitals range from n equal to 3 through 7. The L value for a d orbital is 2 and range from minus 2, minus 1, 0, plus 1, and plus 2 for the M sub L levels. Now, experiments by Stern and Gerlach showed that a beam of silver atoms can be split in two by a magnetic field. And the experiment revealed that the electrons spin on their axes. And as they spin, they generate a magnetic field, because spinning charged particles generate a magnetic field. Now, because electrons with different spins are deflected in opposite directions, the beam was split in two, with part of the beam going to the top of the collector plate and the other half going to the bottom of the collector plate. We know three quantum numbers already. N, the integer 1 through 7. L, designating the shape of the orbital S, P, D, or F, or 0, 1, 2, and 3. And M sub L, ranging from minus L through 0 to plus L. The spin quantum number is designated M sub S and is a fourth quantum number. A spin quantum number describes how the electron spins on its axis, clockwise or counterclockwise. If an orbital holds two electrons, they must have opposite spins. N sub S can have values of plus a half or minus a half, and are depicted graphically as an up arrow or a down arrow. Now, none of this probably makes much sense right now. By the end of today's lecture, all of this should become much more clear. Now, Mendeleev in 1869, ordered the elements by atomic mass. These days we do it by atomic number, but in those days he used atomic mass. And he saw a repeating pattern of properties. And what he did is put the elements with similar properties in the same column and used a pattern to predict properties of undiscovered elements. And when the atomic mass order did not fit other properties, he reordered by these other properties.
The periodic table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitri Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really. That had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitri was making a bold statement. He said, and I'm paraphrasing here, "Y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time: scandium, germanium, rhenium. The element he called eka-manganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitri predicted its existence, 30 years after he died. Dmitri died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendeleevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitri Mendeleev, the architect of the periodic table, will be staring back.
And here's a short BBC clip showing how the properties of elements periodically repeat themselves.
Elements are grouped together in the periodic table. Those shown in green are non-metals. The majority are metals, shown in blue. The metals used in jewellery, copper, silver and gold, are all found in the same group of the periodic table. They are a family of elements and, like most families, they've got a lot in common.
The most obvious thing about these metals is that they are unreactive. If they weren't, they'd react with the air. In fact, copper and silver do tarnish over time.
In the unreactive metals, we move to the more reactive ones. The most reactive metals can be found in group 1 of the periodic table. They're called the alkali metals. The ones you've probably heard of are lithium, sodium, potassium, rubidium and cesium. And you've probably seen many of the reactions of lithium, sodium and potassium in school. Lithium is reactive, so it's usually stored under oil to keep it away from oxygen in the air. It can be cut with a sharp knife to reveal the shiny metal inside. Sodium is similar. Again, it's stored under oil and can be cut slightly more easily with a knife. Potassium is also stored under oil, and it cuts even easier with a knife. Obviously, there are huge similarities here. As we go down the group, the melting point of each element decreases. This is lithium reacting with water, a reaction you've probably seen in class. It's releasing hydrogen bubbles. That's why it's fizzing. This is sodium. The reaction with water produces so much heat that it's melting the sodium. And this is potassium. In this case, the gas ignites as well. So, any bets on how rubidium will react with water? And finally, here's cesium. So, there's no doubt that as we go down group 1, reactivity increases. Lithium is reactive, but cesium is extremely reactive. Like the group 1 metals, there are similarities and trends as you go down the group. They are all non-metals. They are all coloured and they gradually change from gases to liquid to solid as we go down the group. Fluorine is a yellow gas. Chlorine is green. Bromine is a dark orange liquid with an orange vapour, and iodine is a dark purple solid which, if gently warmed, produces a violet vapour. The fluorine is stored in a gas cylinder and it's released through the nozzle.
Fluorine onto roll sulphur.
The flame is caused by the fluorine reacting with the sulphur.
Now we have wood charcoal, carbon, and fluorine reacting with that, and it will burn away. So with iron wool you should get instantaneous reaction again.
Fluorine bursts into flames when it reacts with many other substances. It even reacts with other halogens, like iodine. So, how does the reactivity of fluorine compare to the other halogens in group 7? A simple way to demonstrate this is to see how the halogens react with hydrogen. Hydrogen and iodine react very slowly, so let's try the next halogen up the group. This gas jar contains an equal measure of hydrogen and bromine. There's no reaction unless you put a lighted splint in the mixture. This plastic bag contains an equal mixture of hydrogen and chlorine, but it doesn't react unless you shine a bright light on it. So, any predictions about hydrogen and fluorine? This balloon contains hydrogen and fluorine is directed at it. The reactions with hydrogen clearly show that the reactivity of the halogens increase as you go up the group. Fluorine is the most reactive non-metal in the periodic table. The periodic table is an ingenious way of organising the elements. Not only does it bring together families of elements which are similar, but it also allows us to predict some of their properties. So, if you're looking for the most ferocious metals, try the bottom of group 1. Or, for the most vicious non-metals, look at the other end of the table at the top of group 7. So, what do you think will happen if you react cesium with fluorine?
Now, Mendeleev's periodic law allows us to predict what the properties of an element will be based on its position in the table. But it does not explain why the pattern exists. And quantum mechanics does. It's a theory that explains why the periodic trends in the properties of elements exist. So now we're ready to talk about electron configurations. The ground state of the electron is the lowest energy orbital that it can occupy. And the distribution of electrons into the various orbitals in an atom in its ground state is called its electron configuration. So here's an example of an electron configuration. This is helium's electron configuration. The number 1 designates the principal energy level 1. The letter S designates the sublevel. So it's the s orbital where L, the quantum number L, equals 0. The subscript designates the number of electrons in the sublevel. In this case, for helium, we have 2 electrons in this 1s orbital. Now, when we solve wave equations, we can generate what's called a total radial probability for each orbital as a function of r, the distance from the nucleus. Now, you know electrons are negative, protons are positive, protons are inside the nucleus. The closer the electron is to the nucleus, the more stable that electron is going to be. So orbitals which are closer to the nucleus have electrons which are more stable and of lower energy. Therefore, from this graph, we see here's the total radial probability for the 1s right here. The 2p looks as if it's actually closer to the nucleus than the 2s. The 2s is in red, the 2p is in blue here. And the 2s is actually moved a little bit out. If that were the case, the 2p would be of lower energy than the 2s. But wait, you see this bump here in red? Well, that changes everything. Because what it means is that the 2s electrons have this probability of being quite close to the nucleus. And that means that the 2s orbital is going to be of lower energy than the 2p orbital. Probability distribution of orbitals shows how close they are to the nucleus and determines the energy level of the orbital. So we can map the energy level of orbitals using these probability distributions. The 1s is first and of the lowest energy. The next is 2s, and the next orbital is the 2p. Then the 3s, the 3p, the 4s, and then a surprise. The 3d has a lower energy than the 4p, but a higher energy than the 4s. So first we have the 4s orbital, then the 3d orbitals, then the 4p orbitals, 5s, 4d, etc. The off-bow principle states that electrons will fill up orbitals in order of increasing orbital energy. So the very first electron for hydrogen goes into the 1s orbital. Helium has 2 electrons, so the second electron fills up the 1s orbital with a different spin. So now the 1s orbital is filled. The next electron for lithium goes into the 2s orbital, so its electron configuration is 1s2, 2s1. The next electron is beryllium over here, and its electronic configuration is 1s2, 2s2. You notice that electrons have to have different spins when they share an orbital. So for this 2s orbital, the first is a spin designated with an arrow pointed up, and the next electron coming in has to have the reverse spin with the arrow going down. In quantum numbers, that would show up as plus a half for the arrow going up and minus a half for the arrow going down. Now we're ready to start filling in the 2p orbitals. First comes boron, with one electron in a 2p orbital. Next is carbon, and now we can apply Hund's rule. Electrons will fill in degenerate orbitals, and degenerate orbitals mean that orbitals have the same energy level. So these 3p orbitals here all have the same energy, so we call them degenerate orbitals. And Hund's rule says that electrons fill in degenerate orbitals singly with parallel spins before they begin to pair up. So carbon will be 2p2. The next electron will be coming into this empty p orbital here, 2p3, that would be nitrogen. Oxygen would be 2p4, and that goes into the first p orbital with a spin down designation. The next would be fluorine, 2p5, again with a spin down. And lastly, neon, 2p6. So let's start building up our electron configurations. First of all, hydrogen has one electron, and that electron is going to inhabit the lowest energy level available to it, and that's the 1s orbital. The helium has two electrons, and it must fill in the 1s orbital first. So that's 1s2. Now lithium has three electrons. The 1s orbital is already filled up. The third electron cannot go into that orbital. So the next one available to it at the lowest energy level is the 2s orbital, and that electron resides there. So this can be written as 1s2, 2s1, or it can be written as helium core, which means the electronic configuration of helium. Helium is in brackets, and then 2s1. Beryllium has four electrons, so it has the helium core, and then fills up the 2s orbital. Now we start filling in the p orbitals. The 2s orbital is now filled, and we start to fill up the three p orbitals in n equals 2. So that we have the helium core, 2s2, 2p1. Carbon is going to be helium core 2s2, 2p2. Nitrogen is going to be helium core 2s2, 2p3. Oxygen 2p4. Fluorine 2p5. Neon 2p6. So we now have two electrons in each of the three p orbitals in n equals 2. And we're filled up. The n equals 2 level is now filled. No more electrons can enter that level. Now the next level available to us is the 3s orbital. Sodium has 11 electrons. 10 of them are going to be in the neon core. The 11th is going to be in the 3s1 orbital. Magnesium fills up the 3s orbital. It now has 2 electrons in it. And again, we start filling in the p orbitals. 3s2, 3p1. For aluminum, silicon is 3p2, phosphorus 3p3, sulfur 3p4, chlorine 3p5, argon 3p6. Look at the last electronic configuration in group 1, if you would. Okay? Lithium ends with 2s1. Sodium ends with 3s1. Interesting. And they have similar chemical properties. You saw in the video how they fizzed when They are added to water to produce hydrogen gas. You saw that they're easily cut with a knife, etc. Beryllium, magnesium, both end up with 2 electrons in an s orbital. Beryllium 2s2, magnesium 3s2. So we're beginning to see the formation of a pattern here that the last electronic configuration of elements in a particular group is similar. Boron ends with a 2p1, aluminum ends with 3p1. So the last electronic configuration is in an orbital that's consistent with the previous elements of that group. All right, now let's go to n equals 4. And with n equals 4, we begin to fill it in with potassium, that's the argon core 4s1, and calcium, argon core 4s2. But then we begin to have the transition metals begin to fill up. Their energy level was a little bit higher than the 4s, and therefore electrons flow into the 4s before they start filling in the 3d. The 4p, on the other hand, is energetically higher than 3d, so it begins to fill up after all the d orbitals are filled up in the n equals 3 level. So scandium ends with the argon core 4s2 3d1, titanium 4s2 3d2, vanadium and chromium 3d3, and then an interesting thing happens with chromium. It's not 4s2 3d4. It would rather have a half-filled set of d orbitals. So that's going to be 4s1 3d5. Then manganese is going to put an extra electron in that 4s. It'll be 4s2 3d5. Iron is 4s2 3d6. Cobalt 3d7. Nickel 3d8. And then the same kind of strange anomaly happens with copper, which you might expect to be 4s2 3d9. It isn't. It borrows an electron from the 4s, so that can have a completely filled up set of d orbitals. It's going to be 4s1 3d10, and then zinc is 4s2 3d10. Once you see how electronic configurations fit within the periodic table, it becomes much easier to write the electronic configuration for any particular atom. The first 2 groups represent the s orbital being filled up. If it's in the first row, it'll be the 1s orbital. If it's in the second, it'll be the 2s, the 3s, the 4s. Then, over in the last 6 blocks, we have the p orbital being filled up. P1, P2, P3, P4, P5, P6. When we get to the 3D level, it turns out 3D fills in after 4S does. So there's a little anomaly that causes students no end of grief, because this is not the 4D level. This is 3D right here. And this is 4D, and this is 5D. So the d orbitals are in a row where their n quantum number is 1 less than the principal number for that row. So this is row 4, but this is 3D. This is row 5, but this is 4D. And you just have to remember that. So the transition metals represent the d orbitals filling in. And finally, we have the lanthanide and actinide series, and those represent the f orbitals. So what's the electronic configuration for magnesium? Well, let's go through it. Look, where magnesium is in the periodic table, it's right here. First of all, if it's in the first 2 groups, it's got to be an s orbital. Secondly, it's in row 1, 2, 3, so it's going to be a 3s orbital. Thirdly, it is going to have 2 electrons in it. Sodium will have the first electron, therefore magnesium will have the second electron. So now you have 3s2. The preceding noble gas, or the core of its electronic configuration, is going to be neon. So we have neon 3s2. That's the electronic configuration for magnesium. And of course you could also write this as 1s2, 2s2, 2p6, 3s2. How about this one? What's the electronic configuration of copper? Well, we did this one a little bit ago, and this was an anomaly, right? First, look at copper, where it is. It is in the transition metals. It is block number 9 in the transition metals. So that's the d orbital filling up. The first row of d orbitals is n equals 3, even though it's preceded by 4s. Then you have 3d. And copper is the 9th block over. But for a d4 and a d9, what you're going to have happen is that an electron from the preceding s orbital is going to be borrowed to either half fill in the d orbital, as in the case with chromium, or to completely fill in the d orbital to make it a d10 orbital, as the case with copper. And the preceding core is going to be argon, right? Here's potassium, so argon is right before it. So we have the argon core, 4s1, 3d10. Now let's try this one. What is the electronic configuration of iridium? Well, we look in the periodic table, and there's iridium right here. So its last electron is going to end in the d block. Which row is this for the s? Well, 1, 2, 3, 4, 5, 6. So this is 6s. So this has to be 5d. And we count over from this first element, 1, 2, 3, 4, 5, 6, 7. It is a 5d7 electron for the last electron in the electronic configuration of iridium. It's going to have the xenon core, 6s2, and then 5d7. Which element has this electronic configuration? Krypton core, 5s2, 4d10, 5p4. Okay, let's go to krypton right here. We drop down 1, so this should be 5s, 5s2, and then 4d10 is all of the d block, and then 4 electrons into the p, 1, 2, 3, 4, looks like tellurium right here, number 52. What is the electronic configuration of aluminum? Ion, Al3+. Now a cation, a positive ion, has 3 less electrons than the electronic configuration of the neutral metal. So the way to do this is first write the electronic configuration for aluminum metal. Here's aluminum right here. And that's going to be, let's see, neon core, 3s2, 3p1. That would be the electronic configuration for aluminum. Now we have to throw out 3 electrons to get a cation with a 3+ charge. So we have 3 electrons right here, 2 in the s, 1 in the p. We discard those, and what we're left with really is just the neon core. 1s2, 2s2, 2p6. We say that the aluminum ion is isoelectronic with neon, meaning it has the same electronic configuration. It does not mean that aluminum ion has the properties of neon. Neon is a noble gas and very unreactive. An aluminum ion is a cation. They don't behave alike at all. Well, let's try this with another charged particle, an anion this time. What is the electronic configuration of the phosphite ion? P3-. So first, let's write the electronic configuration for phosphorus. And where is phosphorus? It's right here, isn't it? And so that's going to be neon core, 3s2, 3p3. Neon core, 3s2, 3p3. Now, because it's an anion with a -3 charge, that means it has to have 3 more electrons than protons. It has to gain 3 electrons. When it does that, it's going to fill up the p block. P orbitals can hold 6 electrons. It's already got 3. Add 3 more, and you're at the argon core. So the phosphite ion has an electronic configuration, isoelectronic with argon, 1s2, 2s2, 2p6, 3s2, 3p6. Transition metals tend to lose their ns electrons before their n-1d electrons. For example, 4s before 3d, or 5s before 4d. So what is the ground state electronic configuration of the ion zinc 2+? Well, zinc is right over here in the 3d, right? 4s2, 3d10. And it's got an argon core. Argon core, 4s2, 3d10. It has to lose 2 electrons to become the +2 cation. It's going to lose its 4s electrons before the 3d electrons. So the 4s electrons are out, and what we end up with is argon core, 3d10. What is the electron configuration and 4 quantum numbers for the last electron of rhodium, number 45? So here's rhodium. It has a krypton core, which is followed by the 5s orbitals, and then, of course, the 4d orbitals. And it's block number 1, 2, 3, 4, 5, 6, 7, 4d7. So, describing its electron configuration, krypton core, 5s2, 4d7. Now we're ready to start coming up with the quantum numbers for the last electron. First of all, the last electron is going to be a 4d electron. So n equals 4, and d means that the L quantum number is 2. Remember, S has L equal to 0, P has L equal to 1, D has L equal to 2, F has L equal to 3. But we do have to come up now with the M sub L quantum number. The way we do that is to write a dash representing each of the 5 degenerate orbitals for the 4d level. -2, -1, 0, +1, +2. Now we're ready to start filling them in. We have 7 electrons to plug in here. So 5 of them are going to go in each of the M sub L orbitals. They can't pair up until all the orbitals have at least 1 electron in them. And after each has 5 electrons, we can start to pair up the other 2 electrons with the spin going downward. Our last electron is in a -1 M sub L, and the arrow's going down, which is equivalent to a -1/2 quantum number. So the quantum number is going to be n equals 4, L equals 2, M sub L equals -1, and M sub S equals -1/2. What is the electron configuration and quantum number for the last electron of selenium, SE number 34? So here's 34. We see it is a p electron, 2p, 3p, 4p. It's going to be a 4p electron, and it's going to be 4 electrons into the 4p. If we write out the whole electronic configuration, it would be argon core, 4s2, 3d10, 4p4. So our first 2 quantum numbers are going to be n equals 4 and L equals 1, because our last electron resides in a p orbital. Now we're ready to figure m sub l and m sub s. We have 4 electrons to put in. 3 go into each of the degenerate orbitals. M sub l equals -1, 0, and +1. For the 3 of them, then they begin to pair up with a spin going down, or a -1/2 spin, in m sub l equal to -1. So that's going to be n equals 4, l equals 1, m sub l equals -1, and m sub s equals -1/2. What element has, as its last electron's quantum number, n equals 5, l equals 2, m sub l equals 0, and m sub s equals -1/2? The first thing we have to do is to realize this is a d orbital because l equals 2. And therefore, we have 5 degenerate d orbitals to fill in, -2, -1, 0, +1, and +2. We see that m sub l is 0, so our last electron is going to end up right here in the 0. And we also see that the m sub s is -1/2, which means the spin is going to be pointing down, not up. So, first we put in the 5 electrons with +1/2 spins in -2, -1, 0, +1, and +2. Now we put in 3 more with spins equal to -1/2. That gives us 8 total electrons in this d orbital. So we're in n equals 5, so that's going to be a 5d orbital. D orbitals start at 3. This is 3d, 4d, 5d. Now we count over 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8, and there it is. Platinum is the element that has this quantum number. How many elements could have, for their last electron, their first 2 quantum numbers starting off as n equals 4, l equals 2? Well, n equals 4, l equals 2 is a 4d orbital. This is 3d, this is 4d, and there are altogether 10 elements that share those first 2 quantum numbers, n equals 4, l equals 2, or 4d.